Welcome back to Numberholic. I'm your host, Sajari, and it's always a pleasure to have you here. Today, we're diving into the 16th episode of Proven, Yet Hard to Believe. The problem of squaring the circle asks whether it's possible to construct a square with the same area as a given circle, using only a compass and straightedge. But what if we think differently? Why didn't anyone seriously consider the idea of simply rolling the circle? If we express the circle's circumference as a length, constructing a square with that length should be simple, right? Well, here's why that line of thought didn't catch on. It's because of a famous paradox known as Aristotle's wheel. This paradox appears in Mechanica, a text once thought to be by Aristotle, but likely written by one of his followers. Here's the setup. Imagine two concentric circles, one large and one small. Place the large one on the ground and roll it forward. As it rolls, the smaller inner circle travels along a straight path above. During a full rotation, every point on the circumference of the smaller circle corresponds 1-to-1 with a point along the straight line. So, that would mean the circumference of the smaller circle is equal to that of the larger one. But wait, you say, isn't the small circle slipping? Then let me ask you, if it slips, does that mean a single point maps to two different points? When exactly is it slipping, and when is it not? It may seem simple, but many great minds have wrestled with this paradox. Mersenne, a contemporary of Descartes and mentor to Pascal, once said, "Whether the smaller circle touches the same point twice, or jumps and slips as it moves forward, I could never figure it out. And I don't believe anyone else ever did." Even Galileo weighed in on the issue. In his two new sciences, Galileo begins his analysis not with circles, but with two concentric hexagons. He imagines them rolling, and notes that every time the outer hexagon rolls onto a new face, the inner hexagon must jump across a small gap. He writes, "If a polygon with 1,000 sides rolls, the larger one traces out a segment equal to its perimeter, but the smaller polygon creates a path made up of 1,000 sides, and 1,000 gaps, a discontinuous motion." Since a circle can be seen as a polygon with an infinite number of sides, Galileo argued that Aristotle's wheel contains infinitely many infinitesimal gaps. These voids can't be measured, but they exist. Galileo begins leaning toward a physical, even atomic explanation. But mathematically, a problem still remains. What is the mathematical counterpart to physical slipping? How do we even define such a concept? One common rebuttal to Aristotle's wheel paradox is that the logic behind it is flawed in the first place. So let's flip the scenario. What if we base the rolling motion on the smaller circle instead? In that case, the larger circle's path is now matched to the smaller one's circumference. You can clearly observe that every point on the larger circle now corresponds 1-to-1 with a shorter segment. So, which one is the true circumference? Structurally, this line of argument mirrors Galileo's famous critique of Aristotle's theory of falling objects. Aristotle claimed that heavier objects fall faster. But in Two New Sciences, Galileo counters with a thought experiment. If you tie two objects together, their total weight is now greater, so by Aristotle's logic, they should fall faster. This is a contradiction. Despite many such arguments, I personally find it hard to just accept the usual rebuttals. I find myself siding more with Mersenne. Aristotle's wheel paradox forces us to ask, what is length, really? How do we define the concept of length itself? In this light, can we simply declare, well, they're just different lengths? That would be assuming the very thing we're trying to prove, a begging the question fallacy. Perhaps what we've taken for granted about length is incomplete or even misleading. I believe Aristotle's question needs to be examined on a deeper level. And that might be through the lens of dimension. What are the properties of dimensions? Where do they come from? By exploring these ideas, I believe we can get closer to a true understanding. That's all for today's episode of Proven Yet Hard to Believe. In the next videos, we'll dive deeper into related paradoxes and what they reveal about the nature of space, motion, and mathematics. Until next time, keep exploring, keep questioning, and stay numberholic.